It's now
Okay.
it's being recorded. Be careful of your words.
Okay. So, for anyone watching the recording, sorry you just missed out on a discussion of how I dislike French people. In the scope of mathematics. Anyways, so regarding homework one, I think on the whole, performance is pretty satisfactory. I would say if you got like 15 or below, be careful to understand everything you didn't get right. So, the solutions are uploaded. You can find them. You can find the solutions in stuff channel on Discord. Make sure to go through it and feel free to ask any questions on something you didn't understand. And there's two things I want to say. Okay, yeah. So first is that I think this might be a side effect of you guys are like kind of just excited, but I am seeing like a little bit of tendency in a few of you to write a lot. And so I mean for like a problem where like you're just like giving your justification and the answer is just like logical phrase, that's okay. But be careful of this with proofs, because basically if your proof is long without like needing to be long, you will lose points stylistically. You can check the rubric in Discord, but also it will just be hard to read. So be aware of that. The other thing is I guess this is more of like a general thing. So uh when you're doing logic, be careful. So what do I mean by that? So I noticed like in a few places like you guys like went for kind of like an intuitive approach. Like so for example on uh problem 6, I think some of you guys wrote something that was like almost correct but was missing a tiny detail. So like for example, somebody wrote something where uh, their statement would be correct for uniqueness, uh, but it would be true when there's nothing that satisfies the proposition. So that's not quite right because that doesn't give you you should have at least one element that satisfies the proposition. So it's just little tiny things can trip you up. So it's important to build that intuition in the back of your mind that something's wrong. Something is not 100% right. So just be aware of that. That you always have to be pretty careful when dealing with logic. All right, and that's all I have to say. So Sangjun, feel free to get started.
Great, thank you, Adam, for the introduction. So today we're going to what I think I promised last time, and we're going to talk about sets, and which many of you took maybe 291, or some maybe saw this in calculus. So it may be a little bit familiar, but we're going to today we're going to discuss a lot more about like someone wants to join. Someone wants to join. Hello. All
I
right.
think
Hopefully
it's
they can
funny
join.
how like every time someone wants to join, you just kind of like your brain freezes and like you're trying to
Right.
process that you want to join.
All right. So where was I? Okay. So we're not going to take like a very take the most formal approach to set theory. In fact, we're going to a lot of mathematicians just think of set theory as just naive set theory, and this is going to be like the approach that we're going to take here. It's kind of like you're just kind of like driving a car, right? You don't need to understand what's going on under the hood. Like you don't need to understand the intricate details of what's going underneath the hood till you need it, right? And for most of your purposes, you probably won't need to open underneath the hood, and actually take a look at what's going on underneath. If you want, but maybe you may be interested. And if you are, there is a set theory course in the math department. It's like Math 361 or something, and that may interest you in the future. All right, so let's begin. What is a set exactly? For our purposes, we're just going to say it's an unordered collection of items where each item appears at most once. So in our world, these sets, right? These sets would be equal. Like let's say 2, 1, 3. Okay. If they were lists, on the other hand, they might be different. Okay, but note that like this is called, I think, Russell's paradox. Yes, I think that sounds about right. If the set, right, the set of all sets that do not contain themselves, right, this we're going to consider this collection. Then like, well, in our definition, right, this is a set, right? But is A in this collection? Well, right, if A is not in here, then we have that this A is in here, right? But if A is in here, then it by definition it can't be here. So this is already a contradiction. So this already tells us that like we need to we need some rules that constitute what a set is. And the rules that a lot of modern day mathematicians use is called the ZF axioms. Zermelo Frankel or something. Some
Frankel?
dudes. Frank. It's like FR Frank, and there's other syllables. But we just say ZF, right?
Yeah.
And oftentimes you'll see ZFC, which is ZF plus the axiom of choice, right? But the axiom of choice is actually non-intuitive, or the statement itself is intuitive, but its consequences are very non-intuitive, and it can be very hairy to actually get into for right now. And I promise you, if you do go further in math, you will see it. So, but we are going to just postpone the discussion and leave it for your future instructors to discuss. Okay. So as I said before, we're not going to get into like the giant details of what ZF is, but it might be a good for your mathematical knowledge to actually glance over what ZF constitutes later on. But for now, as you said, we're going to take the approach of naive set theory. Okay, so the common sets that we discuss are Z. We use Blackboard font to denote the integers. Some authors just use just Blackboard, but we encourage that you just use the Blackboard. Did I say Blackboard? I say some authors just use just the boldface, but we recommend that you use Blackboard font and on your homework. I think some people actually just used just the letter Z, or to denote the integers. Don't do this. And the next we're going to the N, right? Which are the natural numbers. It's N for natural numbers. By the way, Z is German for number. Q, our Blackboard Q is the rational numbers, which is the quotient of two integers, where the denominator is 0 or is non-zero. The Blackboard R is the real numbers. We're going to discuss what they are at a later lecture. And the complex numbers, which is A plus BI, as we all know. And H are the quaternions, which we get by introducing more elements whose squares are negative 1. Okay, but these are some common sets that you might see, and these are some common sets that you will use later. So here's the first or second definition, right? So what do we mean when we say something is a subset, right? Intuitively, we should think of a subset, right, as like a set that is contained in another, right? So if A is a subset of B, then it should be completely contained in B, right? So here's how we formalize that notion, right? We say A is a subset of B, right? If for every single element in A, we have that element must be in B, right? And then we write this as with this symbol over here. Okay, you should think about this symbol as sort of an analog to the less than or equal to symbol, right? Where this bar underneath symbolizes the fact that the two sets might be equal to each other. If you want to say that something is a proper subset or a strict subset, you would use this symbol instead, right? Which would imply that A, if you write A subset B, then we know that A is definitely not equal to B. Some authors use the symbol this to denote that to denote a proper subset, but this is not the approach that we're going to take here. Okay, and of course this symbol is the analog of just the less than symbol. Okay, but I just said two sets are not equal, and never actually defined what two sets equal actually means. So here's the next definition. We say the two sets are equal, right? And in this case we would write A equals B when they're subsets of each other. Okay, so if I can contain a set in another set and flip that relation backwards, then the sets are said to be equal. And that's exactly how you are going to and if you want to unpack that definition, right, actually that just says for every A in big A, right? That you can find that in B, and for every guy you can find in B, you can find them in A. So for every element you find in a set, you can find in the other, and vice versa. And that's exactly what we intuitively think about, how we should intuitively think about set equality. Here are some examples of sets. Here we can just describe sets just by listing out elements like this: 1, 2. Sets can contain numbers, or sets can contain not numbers, like code.pdf and $7 signs. Okay, sets can contain sets, right? So sets can contain 1, and sets can contain the set of 2, right? So notice that in this particular set, the set doesn't contain the number 2. It contains a set containing 2. Okay, and here's some more examples of sets, which I will not attempt to read. Are there any questions so far?
Hey, I wrote these sets out for you guys.
It'll be a good exercise for you to think about later. Will we make distinctions between subsets and proper subsets? Yes, we will. And that is exactly what we talked about. Are there any other questions that I might entertain? No. Great. When we are at, I guess we didn't really talk about this. When we talk about sets, right, we can basically have two, we're going to use basically two ways to define sets. And one way is to just list out the elements like this. And the other is to use set builder notation. And that is basically what this notation is, right? For example, we can say if A is this, right? I'm just going to write it out. Right? This is the set of all prime numbers. So what this is saying, that like the first part is saying A is the set of these things, right? These are the things, right? And the second side is the rule in which we in which we decide which elements are in here or not, right? So we say n. This is a set of all n in the natural numbers. This bar you read such that, st means such that n is prime. Okay, sometimes some authors will use a colon instead of a bar, but this is basically what set builder notation is, and that is what is going on over here. Sets can be very scary. R mod q can be scary, and if you Adam is not a mathematician anymore, but if you do pursue further mathematics, you'll almost inevitably run it into R mod q, which is used in the construction of something called a non-measurable set. Okay. All right, here's the next definition. So we just constructed the notion of a subset, right? So the next thing we're going to talk about is the set, or the collection of all subsets of a set, right? Because we just talked about how a set can contain sets, right? But let's be careful about that, because as we said here, right? As we said here, if we just allow anything to be in a set, then we might run into contradictions. So we need to be a little bit careful, but for right now, we're just going to sweep everything under the rug and say, we can only contain sets that are sufficiently nice. And all the subsets, it turns out, are sufficiently nice. The power set, we're going to write P of A, P for power, is going to be the subset, is going to be the set of all actually, let me just write it out. So P of A, right, is going to be this all sets X such that X is a subset of A, right? It is going to contain every subset of A, as we said, and some authors use the notation 2 to the A. I think this is actually used a lot by combinatorialists. So if you see this notation, that's what's going on. And this should actually clue you into what the cardinality or the size of what the set should be. All right, the next thing, the next definition is the empty set, which is a set that contains nothing. We're going to write it as a 0 with a line through it. And as an exercise, you should actually you should also note that the empty set is a subset of any set that you want. And how do you know this? Because in our definition, right? What do we have for any guy in the empty set? We have that guy is in A, but nothing is in the empty set. So the antecedent is false. So that means in our implication, everything is true. More on this type of proof technique will come later in the next lecture. Are there any questions so far? No. What is the difference between P of A and A? Yeah, sure. So maybe we should look at an example. So let's let for the sake of simplicity, let's say A is, I don't want to write something too big, so let's just say it's 1, 2, right? It's a set containing the numbers 1 and 2. And the power set of A, right, is the set of all subsets of A. So what would it contain, right?
Actually, it's a good idea. Maybe you should let them think about it for 30 seconds.
Sure. That's a great idea. It does not contain 0.
Or
contains. I mean, well, if you want to talk about constructions, then maybe it does, right? But,
that's what I was hinting.
Sorry, yeah. Does the power set contain itself?
The power set contain itself? No.
Okay.
Well, what do you mean contain? As an element or a subset? Because there's like 2 different notions of contains. But let's be careful, because the power set of A, right, is not in the power set of A. But if you're using contains as a subset relation, then it is certainly true, right? This is true because every set contains itself in a subset kind of way, but not in an might not be true in an element kind of way.
Let's actually refrain from using the word contains to mean subset.
That's a great idea. Maybe I got into the habit of saying this.
Oh
because,
no.
Because like, I don't know, a lot of books and authors actually do that. So it just
I mean
happens.
Like,
but
if you say like a group contains a subgroup, right? But it gets that word, like lots of words in math get overloaded. So maybe let's refrain ourselves from getting too confused. So I think it might make, I think I gave you enough time to think about this. So I'm just going to tell you the power set contains 4 elements, and from A contains 2 elements. And when we talk about the size of a set, we're going to use this notation, right? And it contains precisely these elements: the empty set, the set containing 1, the set containing 2, and the set containing 1 and 2. Okay, so how did we come to this conclusion? Well, one way to think about power sets, right, is just to kind of think of everything like a bit string. If you have a set of size n, right, in our case, n would be 2, right? Let's say 2, and consider some subset B of A, right? And then let's say the elements of A are like ordered like this, 1, 2, right? And and then basically the power set is going to be represented by all the different types of bit strings, if that's possible, right? So there's 0, 0 represents neither 1 nor 2 is inside a subset, right? For any set, and you can have 0, 1, 1, 0, and 1, 1, right? And 0, 1 meaning 1 is not in the subset, but 1 is, right? That corresponds. 2 is, that corresponds to this subset, right? And 1, 1 corresponds to this subset where both the elements are in the subset. And 1, 0 corresponds to this subset where 1 is in the subset and 0 is not. To be a little more precise, if the ith bit is on in the bit string, then the ith element in the set should be included in the subset you're constructing.
Yeah. Hopefully that made sense. This also shows you that the empty set is in the power set, right? And as we said, the empty set is a subset of any set.
If the empty set is an element of A, do you get 1 less subset in PA? Well, okay, so let's say A is the set containing the empty set, right? So it's the set containing 1 element, and that 1 element is precisely the empty set. Then my power set will have two elements, right? Based on Sungjun's formula, we have 2 to n elements. And the two elements will be, the first one will be the empty set, because the empty set is always in the power set. And the next thing will be A itself, because A is a subset of itself. So we'll get two elements. One is the empty set, and the other is the set containing the empty set in our power set.
Hopefully
So you
that,
don't like get like something fewer. You'll always get the same cardinality when you're talking about these finite sets.
yes. You will actually see an exercise relating to this
Yes.
for you to think about. Okay, so hopefully, are there any other questions? How are we doing on time? I think good. I don't think there are questions, right? Great. So the next thing we're going to talk about is unions and intersections. And we actually probably saw unions and intersections in calculus, right? With interval notation and whatnot. So we'll be a little bit more brief with this. So the union of two sets A and B is all the sets, right? That is either in A or in B, right? And or as in the sense of logical order from last lecture. And we're going to write A, U, B, right? U as in union. And the intersection is the set that contains all elements that are in both A and in both B, right? So we're going to write it as A backwards or upside down U for intersection B. And it's a cup and a cap. Okay. I think most of us or everyone probably saw this in calculus. So let me just do a quick example, right? If A is, let's say, the entire natural numbers, then B is, let's say, the set with 1, 2, right? Then note that B is a subset of A, right? And then A union, what should A union be, and what should A intersect B be? Let me give you 10 seconds to think about it. I think that's 10 seconds. And the union should be N, and the intersections should be 1, 2, right? So here, that was just a quick example. Okay, no questions so far. Great. Again, I think the union and intersection you probably saw in calculus already, so that's why we're being very brief about it. All right, so here's our first proposition. We're going to prove a few subset relations, and the subset relation is this, right? We're going to show that A intersect B for any two sets, right? A intersect B is a subset of A, which is a subset of A union B. So this says two things, right? First, it says that A intersect B is a subset of A, and then it says that A is a subset of A union B. So we are going to need to show both things, right? And we're going to, in fact, we're going to provide some kind of a template to proving subset relations. Okay, so to show the first thing, we need to show that for going back to the definition of what a subset relation was, you might want to flip through it. You need to show that for any guy you find in A intersect B, that guy you can find in A. Okay, and that is just by the definition of set. I don't want to say containment, subset relations. Yes. We're not gonna talk about proof techniques yet, but the general idea is that you need to instantiate a variable. How do I say that? You need to fix any variable, right? An arbitrary variable in this set. And the keyword is arbitrary, right? You know nothing about that element except for the fact that it is an A intersect B, and you're going to need to show that it is an A. Okay. We're going to return to this idea in the next lecture. All right, so let's try that. So let X be in A intersect B, and let is X. And when we say this, there's the implicit notion that X is arbitrary, right? From the definition of what an intersection is, we know that X is both in A and X is also in B, right? Since X is in A, then X is in A, right? And that means that is exactly what we wanted to show, right? And the other part, right? This part is similar, right? You start by assuming that X is in A, right? So let X be in A, right? And X is arbitrary. And how do we know that it's an A union B? Well, if you want to be an A union B, you need to be either an A and you need to be in B, right? But since X is an A, this is true because this part is true, right? So that means X needs to be A union B. All right. Are there any questions about our first proof? Great.
Well,
as an
just to reiterate, so it really sticks. To show a subset, you take an arbitrary element in the first set, and you show that it must belong to the second set. And that shows that every element in the first set must also appear in the second set.
Great. All right. Yes. Maybe as an exercise, maybe it might be a good exercise to show that let's say the empty set union A, or did I say union? I meant intersect.
Yeah.
For any set A, the empty set intersect A is the empty set, and the empty set union A is A. This is not a homework, but it's a good exercise to think about. Here's another here's another example of a similar proof technique. So we're going to show that the power set of A is a subset of the power set of A union B, right? If you have a set in the power set of A, then by definition of a power set, right, then you have X is a subset of A, right? That's because every element of the power set is a subset of A, right? That means, right, if X is a subset of A, then from our discussion here, it must be a subset of A union B. And that we already have that X is inside a power set of A union B. Okay, and from that discussion, the result follows. Oh, I guess I didn't mention this, or it's not really a it's not we didn't really give an example of this. To prove set equality, right, you need to prove this direction and this direction. You need to do that both, right? Maybe if you have time, we'll return to this example. But yes, you should to prove set. So I heard a ping. Someone raised their hand. Open queue. Lower your hand. What do you want to say?
Yeah. How valid it is it to use language like from there it follows that X is in P A union B, like that type of language in a proof?
It needs to be clear. You can use it as long as the step you're taking is clear, right? In this particular instance, right, we are going from this fact to this fact, right? And why can we do this? Well, this fact comes from the definition of a power set, which we have over here, right? It is a set that has for every element all the subsets of that set, right? So if we have a set, right, is in the power set of A union B, if and only if that set is a subset of that element, right? So
can I just clarify
say,
something?
Sure.
Is your question about the phrasing, like literally the English phrase, or is it about the actual step itself?
I guess a bit of both, because I just want to know like when you can use that, because sometimes it might seem clear to me, but it might not seem clear to the person reading the proof.
So that phrase is just equivalent to therefore. The only reason I wrote from there follows instead of therefore is because I didn't want to use the same phrase twice. So then you have a more general question, which is when are we allowed to, make a step? And this is very context sensitive, right? So yes, it depends on what's clear to you and what's clear to someone else, but it's hard to answer. But
the general rule of thumb that I heard was that you should be writing a proof in a class, right? Like in the classroom environment. That in your homework, your proof should be just like how you're explaining to your peers, right? So if you're writing at a level that your peers can understand it, then you're good to go, right? But if you're leaving out steps, right, or you're just saying, yes, A, therefore B, and you're leaving out like a bunch of steps that maybe your peers might not understand, then that's not good. Does that make sense? Maybe
I
Adam
would
disagrees.
say I would say you should be a little careful when thinking like that, because like especially at a lower level, like maybe you say it and like somebody understand what you're saying, but like you can still accidentally skip out a step that should be justified. Do you know what I mean, Sanjay?
Yeah, I guess you're right. Yeah.
Yeah, so I guess you should take as a baseline, like if you just recited your proof verbatim to somebody in your class, would they understand that? But even more than that, you should make sure you go an extra level to justify everything, so that they're really truly convinced that everything in the proof is 100% correct. And I would say so when I said context sensitive, for example, like when you're in 300, everything should be really 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 clear. The reason for this is that, maybe your intuition is right 95% of the time, but to make sure it's right 100% of the time, you need to be really clear and understand everything, because there will always be some trickiness, some low level detail that can escape your intuition. So in 300, we do everything very slowly, very carefully. But as you improve as a mathematician, your intuition will be more accurate. You will have less trouble with such details. You'll get used to these patterns, and so there it becomes more okay to leave out some details. So to understand what is okay, what's not okay, you should try to look at our proofs as an example. So we will show you some proof this lecture, next lecture, and of course every lecture will show you proof, and we will give you feedback on where you should give more detail or less detail, and you should try to learn from that.
Okay. Yeah. Thank you.
Cool.
Hopefully that made sense. Are there any other questions that you want to ask? I think we're doing. Oh goodness, I think we're doing okay on time. But let me check. Yeah, we're doing okay on time, I think. Are there any other
I have a
questions?
question about power sets.
Power
So
sets,
then,
sure.
is it if wait, sorry, I lost my train of thought. Is it true that the power set of A union B would be equal to the power set of A plus the power set of B minus the power set of A intersection B?
What do you mean by plus? We can't really add sets, right? Are we talking
Like
about
adding
unions?
the like uh
So
appending
you're
the
asking.
elements of A and B.
You're
Oh, we
claiming.
don't have a notion of appending, right? We only right now have very few things we can do with sets. We can take a power set, take union, and intersection. That's all we got.
Oh, okay.
So what is the operation you're suggesting?
Like creating a set that has all the elements of A and all the elements of B.
But what about all the elements? So we're not there yet, but you're leaving out a crucial part, I think.
That's why there's a subtraction of the intersection, right? Because you have duplicates.
Sure, but you're still leaving out the elements that are in B but not in A. We're gonna return to this later. Okay, so we're not quite there yet.
Yeah, let's move along for now.
Okay, so the next notion that we are going to introduce is the complement of a set, right? And it's spelled with an E, right? There's no I in our definition of complement. It is the set of all elements of B which are not in A, right? And usually this set B is going to be like the universal set. The largest set that we are considering at the time. I call it the universal set because it's universal. And we're going to write it A to the C for complement. I think some books actually use lowercase c, but who cares? I think like combinatorialists use bar, which is don't do this. And the next definition, this is just for shorthand, right? Bracket n we're going to use to denote the subset of all natural numbers from 1 through n. Okay, so let's look at an example. Let's let our universal set be 4, right? Or going from 1 through 4, right? Again, this is 1 to 4, and let A be 2, 4, right? And then the corresponding bit string is 1 is not in here, 2 is in here, 3 is not in here, and 4 is in here, so we're going to get 0, 1, 0, 1. So now the bit string of a complement is obtained by flipping all the bits, which means if you see a 0, turn it to a 1. If you see a 1, turn it to 0, right? And then we get 1, 0, 1, 0, which tells us that our complement is 1, 3. Okay. All right. And I'm going to reiterate again, when we're taking complements, right, the complement depends on what your universal set is, right? In our example, the universal set was the subset of natural numbers from 1 through 4 was 1, 2, 3, 4. But if our B was like n, right, if it was like all natural numbers, right, then we would have 1, 3, 5, 6, 7, 8, 9, and so on, right? All right. Hopefully that made sense. And if you recall from last lecture, we had De Morgan's laws, right? And we can have De Morgan's laws for sets, right? If you have some universal set U, and then A and B are in U, then complement kind of work the same way as they did from before. And I believe someone, I don't remember actually who, posted a very nice diagram of like Venn actually, or are they called? I think they're called Euler diagrams, not Venn diagrams, but something like that. About like how De Morgan's laws works with sets. So maybe if you could look at that to give like a proof without words, to what is it? To maybe think about it. But again, that was not like a formal proof. To prove it formally, right, you would need to show set containment in both directions. Okay, I'm gonna pause here. Are there any questions? Okay, I don't think I see any questions. All right, so great. So we talked about the idea of complements, and we talked about De Morgan's laws. Great. So the next thing we want to, so we just talked about any finite number of sets, right? You can just union things together, right? So if you have like if you have like sets A1 through AN, right? Then you have then you can just union these all together, right? A1 union A2 union A3, right? Dot 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 through AN, and we kind of you can kind of think about this. You can write this out, but we want like a more compact notation. Or maybe we want to extend this to the idea of like infinite unions, right? All right, so here's our next definition. An indexing set, right, is, as you can kind of guess, is any set where you can use to index some collection, right? So that means you can assign numbers to each set. In our case here above, in our collection of sets A1 through AN, our indexing set would be bracket n. Okay? And for like a series of for a sequence, right, of like this, for a sub little I equals 2 to the I. So this is like the sequence 1, no, not 1. Our for a sequence little here, A1 would be like 2, A2 would be 4, etc. So our sequence would be 2, 4, 8, and so on. So you might be able to index. So you might in index you can just think of it like you're assigning each element in the set a number. Okay. Okay. So now we're going to union. Now we're going to take this index set and we're going to union all the elements in that index collection. And that's exactly what the definition is here. An indexed union is the set A, all the set in U. This is the universal set, right? Such that we can find an index such that A is in A little I. I guess we never. All right, so the notation we're going to use for an indexed union, right, is if big I is the indexing set, then we're going to write big union, the big U, right, where I is an I of AI. Okay, this is the notation that we're going to use. And in this case, right, in this example that I cooked up above, you might write it like this, where n, or not n, because I already used n, where I'll say j goes from 1 to n of aj. Okay, something like this. And this big I over here is just like a placeholder for other indexing sets. Most often, you're going to use like big N or natural numbers as your indexing set, but these indexing set can be basically be whatever you want, right? They can be Q or R, right? So if you have a sub little I, right? Then here's an example. Define, let's say a sub little I is going to be the set containing 2 times I plus 1 for I in the natural numbers. What is the union of all such AI? So remember, each AI is like I guess it's singleton. Maybe I'll give you a few seconds to think about it. I have a question. Is it valid to think of AI like a function of I? Yes, right? Yes, because every sequence is a function, but we're going to return to this idea a little bit later. But yes, it is true. For every index you get, right? For every index, there's a little machine. You input an I, right, for an index, and then that machine would spit out the set a sub I. Okay.
Well,
Does that make sense?
we can be even more formal, right? We can say this function has a type, right? The input type is I. It's an element from I. And the output type is an element from some power set, right? So for example, if the output sets all contain natural numbers, then the domain of this function would just be the power set of n. Did I say domain? The codomain of this function should be, the codomain of this
so
function.
The domain would be
power
the
set of n.
indexing set. The domain would be indexing set. You can well, yes, I guess I was being a little bit silly. They might not be sequences because the indexing set might not be a natural number. But if it were a natural number, it would be a sequence. But we're going to return to that idea.
What's a codomain? So your high school
Oh,
teachers failed you, unfortunately. So they call it the range of a function, right? The thing you're mapping onto. But that's not what we call it. The range is everything that gets hit in the codomain. So I mean, just briefly say, for example, if we take square root of the absolute value of x, and the domain is R, and the codomain is also R, then the range will be, well, it would just be the non-negative reals.
It's okay if you don't immediately wrap your head around it, because we're going to return to this idea in lecture 7.
Yeah.
6? No, 7.
Yeah.
Winston Kwan has raised a hand.
Hello, Winston.
Let's lower your hand. Do you have a question?
Yeah,
I think
so-
also,
Oh, go
sorry,
ahead.
they can lower the hand by themselves, just so you know.
I want to be very forceful. Go on, please.
So whenever you take a subset, you get an empty set, right? Or
Say that again?
whenever you take like you define like a subset of a set, you tack on another element, which is the empty set, right? That's what you guys.
I'm not quite following what you're trying to say.
Neither am I.
Just going back to the empty set. You guys said if we take like the empty set or the subset of an empty set, you would get 2 like empty.
The subset of an empty set?
Yeah.
Where did we say this? I'm sorry.
Wait.
You maybe.
So also,
John
I
might
think
know
something
We had
that's
earlier the
Yeah, go ahead.
subset of a set which has the empty set.
Oh yeah, maybe I'm miswording it, but
every
Well,
set has the empty set as a subset. Is that what you're talking about?
right. So would it be that if you take the index of a subset of a set, it'll never be equal to each other? Because you always add on the empty set.
I'm still not quite following what you're saying.
neither am I. Can you give me an example?
It was when Vopal asked the question of if the empty set is an element of A,
The empty
that
set is
com-
an element of A. Yeah. If the empty set is an element of A, right? Maybe I'll write it down over somewhere here. If A, right, the example was the set containing the empty set, then the power set of A was the empty set itself and the set containing the empty set, right?
oh right, sorry, the power set. I misspoke with subset.
Okay,
So the
what were
power
you saying?
set. So the index of the power set can never be equal to the set A. The
Oh,
index of set
when
A.
you're saying index, you're talking about the size, right?
Yeah.
So size. We'll hold that thought. We'll come back to that.
Okay.
He's got something. He's got something
I read
cooking in the pot.
I
some
remember
shit.
the lecture notes. Okay.
Okay. But did everyone I hope that was enough time to think about this example over here. Did everyone did everyone get a chance to think about this? Are there any answers in the chat, or should I just say it? I don't think I see any answers. I don't think I see any takers. So the union, I would say, is I'm just gonna list them out. So I can be, let's say, can I be 0? No, not in our world, right? So we're gonna start from I equals 1. So you get 3, 5, 7, 9, etc., right? Which is the set of all odd integers greater than 1. Okay, does that make sense? Okay, I'm going to assume that I made sense since no one has any objections. And when z is equal to, when the indexing set was z, we're just going to get all the odd integers. And when you have q, right, you're just going to get, what are you going to get? I think you're just going to get every single rational number possible.
Yep.
And similar with r. Okay, does that make sense? And similarly, right, since we talked about an indexed union, why don't we just talk about its like its sibling, right? Its twin, the indexed intersection, right? We're going to whereas in the indexed union, there was an existential quantifier attached to it. In the indexed intersection, there's a for all, the universal quantifier attached to it, which just says that like this is the set of all A in the universal set, such that you can find it in every single guy in the indexed collection. So you'll write it like this with a big upside down U, right? We're gonna write it like I in big I of AI, right? And that is what the indexed intersection would be. Great. Yeah. Okay, so the next thing we're going to talk about is the set difference, which I think someone alluded to earlier. I don't remember who. Okay. The set difference of two sets is every element of A that does not appear in B. So if we are to draw a diagram, right, it's always instructive when we're doing set theory stuff to draw diagrams. So let's say we have two sets A and B, right? A and B, then the set difference, right, would be this set over here. Like, let me just draw it, right? This would be that set that I highlighted would be A set minus B. It's everything that's in A but not in B. Okay? Did that make sense? You can describe it as all A in A such that A is not in B. Or if you have some notion of a universal set, you can also write it like this: A intersect B complement. Okay? And this way of thinking is useful in measure theory. Okay, as an example, we're going to give you an example. If A is the set from 1, 2, 3, 4, and B is 3, 4, 5, 6, right? Then A minus B is everything that's in A but not in B, right? So 1, 2, 3, 4. Everything that's in A but not in B is 1 and 2, right? So it's the set containing 1 and 2. And B minus A is everything that's in B that's not in A, which is 5 and 6. Okay. Are there questions? Okay, I don't think I see any questions. Looks like I'm doing fantastic on time. The next notion we're going to introduce is the Cartesian product, right? Or the direct product, I think. It's basically just you have two sets, right? And then you just smush them together, kind of. It's basically all the pairs, right? It's basically the set of all ordered pairs. It's a set of all ordered pairs A comma B, such that A comes from A and B comes from B. Okay, and we're gonna write it as A cross B. Okay. But if you wanted to do so if we look above, right, we can describe unions as we can string together unions, right? But what if you wanted to have something like what if you wanted to string together like products, right? Would you like associativity? Would you have like would you associate it like this kind of? But the answer is that like the convention that we use is we're just gonna string together all of them, like as like n tuples. That's called flattening. You know, I've actually never seen the word flatten outside of like a computer science context. Honestly, like I think I've only seen this in like NumPy or something. But like this is but by convention, right? This would be like then A1 cross ... cross AN, right? Would be this would be an element of this set. Okay, as an example, the set of all tuples, right? Two tuples of the real numbers is R cross R, right? So and that is that's just the 2D plane, right? And we write that as R2. Okay, you can think about it as the Cartesian product of Rn itself. But maybe I'll comment a little bit. Once you start putting different structures on the real numbers and different structures on the plane, it might not be like a trivial thing to verify that when you like when you take the Cartesian product of two structures, that you need to check that when you take the Cartesian product, that it's actually the same thing as the structure that you put on R2. In particular, you might be thinking about like maybe some topological structure or like some analytic structure, like a sigma algebra.
Hey, don't scare them.
So then what if A has more elements than B? For which example is this? Is this for Cartesian product or for set
Yeah, for
reference?
Cartesian product.
For what if A has
What?
more elements than B? Sure, let's look at it. Let A be 1, 2, 3, right? And let's say B is like I don't know.
Just do 1, 2.
Sure, 1, 2. Okay, then let's look at an example. So you say clearly A has more elements than B, right? Then let's write out, this is simple enough. Let's write out A cross B. This would be the set, right? 1, 1, 1, 2. Yes, I didn't screw up. Oh my, I was like, wait. I thought I screwed up. 2, 1, right? And 2, 2. 3, 1, 3, 2.
Okay. No,
Did that make sense?
Yeah. I was thinking of it as in like it would just be 1, 1, 2, 2, and then 3, like nothing.
Well,
No. It's
notice
all
that
possible tuples.
if you
Okay,
wanted to do something like that, which is similar to zipping in Python, we don't even have an order, right? So you've assumed the natural ordering on numbers, but sets are unordered collections, right? So B, we've written 1, 2, but B is also equal to 2, 1.
Oh,
Right? Remember this discussion earlier when I said
Also, I
right?
actually
I
very
said
very
1,
importantly,
2,
I
3 is
should
equal to 2
clarify.
and 3.
Oh yeah, you said that. I think someone else also mentioned duplicates, but also notice the set
Did someone say
1,
that?
1, 2. Yeah, someone said something about like you have to remove duplicates or something, but the set 1, 1, 2 is equal to the set 1, 2. Because duplicates don't they
Don't
don't
count.
mean anything in a set.
okay. Thank you.
And you can actually to verify that these two sets are equal, you can just go back to the idea we presented in definition 2.4. Okay. Hopefully does that make sense? Are there any other questions? Are there any other questions? Okay, I don't think I see any questions. So the next idea that we're going to talk about is the cardinality of a set. The cardinality is basically the size of a set, and we're going to write bar to denote size, because when you put a bar around something, it usually just denotes the size of something. I think some professors just use like card of A for cardinality. This is not the approach that we're going to take. For example, the cardinality of the empty set is 0, right? Because it has no elements. If the cardinality of a set A is n, then the cardinality of the power set of A is 2 to the n. And you might want to think about this in the sense of bit strings that we presented earlier. Okay. So for infinite sets, we're not going to talk about it right now, but we're not going to talk about cardinality of infinite sets right now. That's going to be for a lecture, I think, 8 or yes, 8. But we're going to come back to this idea. But Cantor proved a very remarkable theorem that just says the cardinality of the power set of a set is strictly greater than the cardinality of the set itself. Okay, and for finite sets, we just showed in our example, we just told you actually in our example that it's fairly clear that usually n is bigger than 2 to the n, or no, 2 to the n is bigger than n, right? Right? But to prove for infinite sets, you're going to need some more tools in our toolbox. But I promise we will get to that later. That's everything that we have actually prepared. So if no questions, then maybe you might want to look at some examples or questions that you might want to have. I don't think there are any questions. So maybe I'll just give you some things that I actually promised that I would give you. So let's look at this empty set. Let's look at this thing. Empty set intersect A, right? Is the empty set. Since I promised I would talk about that later. So, yeah, no space. So claim, right? The empty set intersect A is the empty set, right? So remember, right? So to prove this, you need to show set containment in both directions, right? You need to both show this and you need to show this, right? So I'm going to call them directions because they're kind of directions, right? So let's start by proving, I think this direction is easier. Okay. So to prove this direction, what do you need to show? You need to show that if X is in the empty set, then X is necessarily in here. Okay. Suppose, right? X is in, what am I saying? Suppose X is in the empty set, right? All right. But the empty set contains no elements, right? So this, actually, I think it might be best phrased this way. So we want to show, right? What do you want to show? We want to show that if X is in the empty set implies, right? X is in the empty set and A, right? Okay, but since the empty set contains no elements, this part of the implication is false, right? So that means whatever you have here doesn't matter, right? Since the antecedent of the implication is false, right? So that means the implication itself is true. Okay, does this make sense? This is the same idea as implication from the previous lecture. Is that okay? Can you repeat that last part? Which part? So if we have the antecedent, right? Antecedent, which means the first part, right? The first part of the implication is false, right? Then we have the entire implication is true because there was the promise was not broken, right? There's nothing in the empty set anyway, right? Does that make sense? So that means the entire implication is true. This is in fact how you would show that the empty set is a subset of every set. You can just prove this direction by saying the empty set is a subset of every set. Okay? Does that make sense? Okay. Here, the other direction is actually far more simple. We actually proved, right? We proved above, right? That any set intersect another set is a subset of the original, right? Look, so this direction is actually easy. Just look above. Does that make sense? And we proved both directions of the set containment, and we have a result. Did that make sense? Are we all on board with this this claim? So yeah, that would be this would be some example of of a showing set equality. Actually, let me write a note here. Note, right? You can also, well, actually never mind, because this was an example. We can also appeal to, I was going to say we can also appeal to the fact that the empty set is a subset of every set, but we already this would be showing explicitly that this is true. Are there any other questions? Or the proof for the union, the other claim, is very similar in the fact that like this claim, empty set union A is equal to A, is very similar, and we'll leave that for you to do. Is there anything else that I might do? I think I heard. Okay. Were there any other claims that I made without substantiating it? Well, yes. Okay. Here's the other claim that I will prove. If A intersect B complement is equal to A minus B. And to prove this, you would prove both directions of the set containment again, right? And actually proving this is actually just an exercise in looking at definition changing. So this to do this, let's say suppose, right? Suppose X is in A, or what am I saying? Suppose X is in A, intersect B complement, then, right, X is in A and X is in B complement, and then, right, X is in A and X is not in B, right? But notice in our definition of set minus or set difference, right, we have X is in A and X is not in B, right? So X is in A minus B. Okay. The reverse direction is actually very similar. Suppose, right, X is in A minus B. Then X is in A and X is not in B. So X is in B complement. So X is in A intersect B complement. All right. So here's another example of how you would show set equality. It's very simple, and actually also note that in my little proof here, right, I didn't use any of the logical symbols that we introduced last lecture, right? I didn't use this. I didn't use this, or this is fine, I guess. It's not terrible, but I didn't use like the quantifier symbols, right? Right? I didn't use these symbols. Don't use these symbols in your formal write-ups. Okay? This is a warning that I'm gonna give you right now. Because if you use these symbols in your write-ups, in your proofs, right? It hurts readability, and your proofs are ultimately going to be, for other people to read it. In fact, the graders are going to read them, right? These symbols are more to elevate understanding for your own self. It's more like a shorthand, right? I think I actually in the PDF about like how a good mathematical writing. This is one of the tips they give you, and you should have already read it, but I'm going to reiterate again. You should not be using like these logical symbols in your formal write-ups, okay? So something like this, right, should be kind of serve as a model about maybe what a proof should look like in our beginning steps. Are there any questions? Stupid question, but is 0 included in natural numbers? Some people say no, and some people say yes, and some people say no. But what should we consider?
The answer is never.
In our convention,
Never.
in our convention, we will not include 0 in the natural numbers. Okay. There may be some instances where it's convenient to include 0. There may be some instances where it's not convenient to include 0. But in our convention, we will not include 0 in the natural numbers.
Simply, if you want to make a statement about all the non-negative integers, for example, you can write. Well, let me write the LeafPack actually for you.
I think if you want to include 0, I think some people
can do
use this.
I've just done it.
Oh, you use superscript.
I will use either. I don't really care.
Yeah, I think I've seen the subscript most often, so you can do something like this.
Gotcha. Okay. Before I forget, here's an exit survey. Make sure to take it. It's literally the same as last time. But so we can get some feedback on the lecture. Oh, actually, it's not literally the same. I adjusted question 2 a little.
The cardinality of the set A is equal to, yes, that I only see one element in that set. That is, the cardinality of that set would be 1.
Here's a dumb way to check. There's 0 commas, so there's 1 element. Although I guess if the comma appears inside a nested set, then bad things happen. Okay, let's not check like that. Yeah, wait, hang on. What the hell is this?
So the cardinality of that thing is still 1, right?
Which thing? Volpo's thing?
Yeah, Volpo's thing.
Well, what the hell is that?
It's
like
the
not
set.
syntactically.
It's a set
correct.
Containing a set with a comma in it, right?
That's not a set. I've never seen commas.
Well,
are
no,
not
like
elements.
if your set is just a comma, right?
No, you can't do that. The breaks syntax. Then like,
it's a string.
What is this then, huh?
It's the string. It's the set containing the string of 3 commas. Right?
I hate this. Okay, guys, don't do.
But
don't ever do this.
recall in our definition, sets can only contain things that are sufficiently nice. And why don't we just define away that these pathological things that you defined, they're not sufficiently nice. I don't take computer science. This hurts my brain.
Okay, this is better. Now we have strings. This is okay.
All right. Are there any other questions? Right. All right. I think I'm going to stop the recording now. What's the cardinality of 1? Okay, so that's actually a non-trivial or not. It's a more interesting question. The cardinality of that thing is 2, right? Yeah, it has 2 things. It contains a set containing 1 and 2, and it contains 3. Well, that's 2 things. Are there any other questions? The cardinality of the power set of an empty set is 2. Is it? You're going to return. Yeah, you're going to return to that idea in your homework. So maybe.
So feel free.
Maybe I wouldn't. Yeah, I'm not gonna spoil the answer.
Feel
We
free
can
to sit
discuss
down
this.
and bash it out.
Yes. All right. If there are no more questions, I'm going to stop the recording. Stop recording.